In the second problem, we have the number of gallons P of t of a pollutant in a lake changing at the rate of P prime of t is 1 minus 3 times e to the negative 0.2 square root of t gallons per day, where t is measured in days. There are 50 gallons of pollutant in the lake at time t equals 0, and the lake is considered to be safe when it contains 40 gallons or less of pollutant. Part A asks, is the amount of pollutant increasing at time t equals 9? Why or why not? Well, the pollutant P of t will be increasing at t equals 9 if P prime of 9 is greater than 0. So we have the formula for P prime of t. We're going to plug that into our graphing calculator, evaluate it at 9, and see if it's positive or negative. So we open up the graphing calculator, we go into y equals, and we've put the function in there, 1 minus 3 times e to the negative 0.2 square root of x. And to evaluate that at 9, we're simply going to go back to the home screen, go to variables, to y variables, to the functions, and to y1. And by putting parentheses with a 9 inside, we can treat that like a function. Evaluate the function stored in y1 when x is equal to 9. And we get negative 0.646. And since P prime of 9 is equal to negative 0.646, we say that P of t is not increasing at t equals 9. And so that answers part A. For part B, we want to find for what value of t will the number of gallons of pollutant be at its minimum, and justify your answer. Well, we're actually, even though it doesn't say it, we're looking for an absolute minimum, the actual lowest value of pollutant in the lake. And because we're not working with a closed interval for time here, we cannot apply the extreme value theorem directly here. Although there are some parameters that we can look at. We're starting off at an amount of 50 gallons of pollutant, and we're going to go down to a minimum of possibly 0 gallons of pollutant. So our value has to be somewhere between 0 and 50, but we don't know at what time it will be. So what we need to do then is to find out if there are any relative minimum critical values in the interval. And actually it's an open interval starting at t equals 0 going to the right. And so I state that P of t has a relative minimum when its derivative P prime of t changes from negative to positive. Since we have P prime of t already in the graphing calculator, we can go out and take a look at its graph and see if it ever changes from negative to positive. So I open up the graphing calculator, I have my function, my derivative stored in y1. I can go to zoom standard, which gives me a negative 10 to a positive 10, 10 by 10 window there, and I can see that in that interval it doesn't cross over. So I may want to adjust my window to go from time 0 maybe out to time 100 by tens, and see if I can find a place where it does. It does cross over, and I can easily see where that's going to happen. I'm going to shrink my y range just a little bit there to go from negative 5 to positive 5, and see, there you go, and I'm going to try to find the 0. Second, calc, option 2 for zeros, the left bound. Now I can either use the arrows or I can type in a number, for example 10, that will put me over to the left, and then the right bound I can put say 50, that'll put me there, and then guess, and it finds it to be at 30.174. And so I write down that this occurs at 30.174, rounded to 3 decimal places, days, or roughly after a month. Now since the derivative is negative prior to that point and positive after that point, then that's going to have to be the absolute minimum. And I'm going to close the calculator. And I say since the derivative is negative for t less than 30.174, and the derivative is positive after that, then the absolute min value occurs at t equals 30.174.